Okay, you are all welcome to this prelude section of petrophysical analysis, which is part of formation evaluation. So we are going to, for the first day, have a brief introduction about petrophysical analysis. Then for day 2, we are going to go into a little bit of practicals, that's software. So I hope everyone downloaded the software and probably you have installed it by now. So we have also included a sample data set that we are going to use tomorrow for the software practicals. Okay, so if we start, so if you can see my screen, I hope you can all see my screen. Please indicate if you can see my screen. All right, thank you. So what you can see on the screen is a 3D model of a reservoir and how a wireline log is carried out. If you look, you're going to see equipment and you're going to see sensors that are tied up to a wire that is sent into a well where measurements are being taken. So first of all, let's look at the life of a well. The life of a well starts from planning to drilling, completion, production, and abandonment. I'm very sure that most of us must have seen this in class. Most of us must have seen this in class. So this is the content of what we are going to do. We have basic concepts, the definition, the borehole parameters, formation evaluation, wireline logging, field operation, qualitative log interpretation, and interpretation workflow. So the first question we are going to ask ourselves is, why do we use logging in an oil and gas industry? Why do we use logging? Because you have to know that logging first is one of the ways in which oil and gas company get direct information from the reservoirs. Because first, they have to first of all start by carrying out a seismic. When they must have demarcated an area, they now go into how they can get direct information from the reservoir. After drilling, of course, they must have done maybe things like measurement while drilling and stuff like that, but they want to get good, accurate measurement of reservoir properties. So they now go into petrophysics. So they have to identify the geologic formation, they have to identify the fluids and the types of fluids found within the reservoir and even the volume of fluid. They have to do well log correlation to see how that area is correlated with one another, to see how the various reservoirs extend laterally. They have to determine the types of fluid that is present. Do we have oil? Do we have water? What amount of oil? What type of oil do we have? They have to optimize well construction and hydrocarbon production. They have to identify a reservoir, define total and recoverable reserves, evaluation of productive capacities of the reservoir. So the first thing I'll first of all want us to look at is, let me share this. I want us to look at is, all right. Can you see my screen? Please indicate if you can see the screen. All right. All right, so what we have on the screen is the borehole environment, how it looks like after drilling must have taken place. After drilling must have taken place, we have what we call the invasion effect. This is one of the things that you have to understand before you go into petrophysics, because one of the most primary way to control the well is to ensure that the mud fluid pressure is greater than the reservoir fluid. Because while drilling, drillers don't want the hydrocarbon or whatsoever is inside the reservoir to get into the borehole. Please let me admit. All right, so drillers don't want what is inside the reservoir to get into the borehole. So to ensure that that doesn't happen, they have to make sure that the drilling mud has a pressure that is greater than the formation pressure. So this drilling mud pressure now stops the hydrocarbon or the fluid inside the formation from flowing into the borehole. But in doing that, they now create another problem that they now have to handle later on. Because once the mud pressure is greater than the formation pressure, part of the drilling fluid now penetrates into the reservoir. If you can look at what you have on the diagram, I hope everyone can see the diagram. All right, okay, thank you. All right, so when you look at the diagram, you realize that we have our reservoir. We have our reservoir here. Please hold on, it's like my PowerPoint is not showing. All right. So when you look at what we have here, you realize that this is what I'm talking about, the invasion effects. So once the mud pressure is greater than the formation fluid pressure, the fluid from the mud now penetrates into the formation, infiltrates into the formation. Because definitely fluid always have that ability to flow from a region of high pressure to a region of low pressure. So if the formation pressure is lower, the fluid formation pressure is lower than that of the mud fluid, what will happen now is part of the mud fluid will penetrate into the formation, infiltrate the formation, and contaminate the zone around the well. In doing that, as part of the fluid from the mud, because we know how a mud looks like, it's a mixture of water, clay, and so many other things added together. So as part of the fluid infiltrate into the formation, the clay part of that mud now tampers around this area of the formation, forming what we call the mud cake. So if you look at what we have here, we have the mud cake that is formed here, and then the fluid now must have penetrated into this region. This effect now is what we call the invasion effect. So we have the invaded zone around the borehole, we have the invaded zone, we have the transition zone, and we have the uninvaded zone. This uninvaded zone now is the area where no drilling fluid has infiltrated to. So this area is where sorry about that, the network. All right, sorry about that, network issues. So I've taken time out to explain about the concept of invasion, what happens to the formation during the process of drilling, because that invasion effect takes place during the process of drilling. So now what I'm going to do now is just to give a rough classification of well logging. What are the various types of well logging? What do they actually measure within the formation? And what information can they give at the end of the day? before we go into any other aspect. All right, so we have our well there. What happens is we have a wire line and we have a sensor that is attached to its wire line. This sensor is to measure the formation property. That's what well logging is all about, to measure the formation property. So they take the sensor right to the depth of the well, and then they bring it up gradually at a predefined speed, and then they now measure the formation property as the sensors is being dragged up from the well. That's one thing you have to note here. The measurements are made when the sensor is being dragged out of the well. All right, now there are various properties, so many properties that the formation that these sensors can measure. So we are going to first of all look at the resistivity of the formation. We are going to look at the density. We are going to look at the gamma ray, that's the natural gamma ray. We are going to look at the neutron. All right, once you have a log that has these 4 basic laws, it is good enough for you to define that well in terms of the hydrocarbon capacity, in terms of hydrocarbon potential and all of that. We have so many other logs. We have so many other logs that will give us better approximation to porosity permeability more than these ones, but these are the basic ones that they first of all start by measuring before they can go now to more complicated logs. More complicated logs, we may have maybe the capsule cross section, we may have maybe the carbon oxygen, we may have the carbon oxygen, we have the nuclear magnetic resonance, we have the nuclear magnetic resonance. These are other logs that can be measured, but these ones are the basic. If you want to go deep into it, you need now to get delta T. You now need to get delta T, which is the transit time. You need now to get the spontaneous potential. You need to get the caliper. But once I have this 4 log, it is sufficient for me to define that particular area, to define that particular well in terms of the hydrocarbon potential. So I'm going to start up with resistivity. We know that resistivity is inversely proportional to the conductivity. This means that if the formation conducts highly, then it means that it has a very low resistance. It has a very low resistance. If the formation doesn't conduct, that means if the conductivity reduces, the resistance does what? The resistance does increases. So all of this depends on whatever we have inside the formation. So what do we expect in the oil and gas company to be inside the formation? We expect water to be there. Water must always be there, even if there's oil or gas or whatsoever, water must always be there. And then we have our oil, and then we have our water, we have water, oil, and we have gas, All right. So water has a very high conductivity. That means it conducts electricity well. So if we have a formation that contains mostly saline water, let me use the word saline water here. That means it has a lot of salt in it, and this salt definitely has ions. These ions can easily conduct electricity. So if we have saline water that conducts electricity, it means that this saline water is going to have a very low resistivity. So just by looking at the nature of the resistivity, is going to tell me what type of fluid I expect to have inside that formation. Oil and gas, generally, we call them hydrocarbons. and hydrocarbons have very, very low conductivity. They have very low conductivity. It means that the resistance is very, very high. It means that the resistance of this hydrocarbon is very, very high. With gas, the highest having the highest resistance. So the problem, one thing that resistivity log always has to pose is that you have to first of all start by identifying or doing a literature review about the basin that you're dealing with before you go into all of this. Because you might go to a particular area and you see a high resistivity, there, and then you are now expecting that because this resistivity is high, I expect to be having hydrocarbon around that area. It doesn't necessarily mean so. Let me take an example like in the Niger Delta Basin. In the Niger Delta Basin, we have three formations. We have the Benin Formation, we have the Abada Formation, and then we have the Akata Formation. The Akata Formation is where the hydrocarbon is coming from. That's our primary source rock. And then here we have our reservoirs, because we have sandstones, and then we have shales there. So the this is probably, if this is our shield, this is our shield. So the sandstones now, above the sandstone, we have a shield layer. That is acting as both a source rock and a sea rock. That means if any hydrocarbon migrate from the source rock into this reservoir rock, we expect trapping to take place because there is no way for the hydrocarbon to escape to the surface. But in this Benin Formation, what we have is totally sandstone. But it doesn't necessarily mean that these sandstones are reservoirs. Because even if we have some small amount of hydrocarbon that will migrate into the Benin Formation, the hydrocarbon, there will be no seal to hold this hydrocarbon in place. So they will definitely escape. But that is not the primary reason why the resistivity in that particular area is high. The Benin Formation is made up of mostly fresh water. It's made up of mostly fresh water. And we know that fresh water have a very, very high resistivity. So because the resistivity is high, I don't just conclude that I have a reservoir in this particular area. I have to go back to my literature review to know the stratigraphy of that particular basin, to know if in this at this particular depth, I can easily have a reservoir. Because if you are not talking about the Abada Formation, then there is no way you should be mentioning a reservoir. So the fact that the resistivity is high does not necessarily mean that you must have hydrocarbon, because most students, what they do is once they see the well log, immediately they see high resistivity, they just say, oh, we have hydrocarbon in that area, without actually verifying from the stratigraphy if we can have a reservoir in this particular area. Because a reservoir here, definitely, I'm using the word reservoir and sandstone differently. Sandstone is just the lithology. But if the lithology contains hydrocarbon, sufficient amount of hydrocarbon, we can now call it a reservoir. That's why I'm now using the word reservoir, and I'm also using the word sandstone, so that just explain so that you don't get confused. So just by looking at the resistivity log, I already have an idea of what type of hydrocarbon I have in that particular formation. I already have what type of fluid. First, let's forget about what type of hydrocarbon. The first question is what type of fluid? Am I having water? So am I having water or hydrocarbon? Am I having water or hydrocarbon? All right. The next, I'm just giving all this so that once we are going down, when we meet these things, we just go through it faster and we just go to the next slide. So that's why I'm giving all of these concepts so that you understand it better before we get there. So the next one now, what I'm going to look at first now is the gamma ray. The gamma ray. Gamma ray measures the natural radioactivity in the formation. It's a measure of the natural radioactivity in the formation. So it's a natural phenomenon. It measures natural phenomenon. You don't need any source to send in any information into the reservoir. Okay, so once we'll go down, we'll see these things, and then let's explain. Let's go gradually so that you see the thing and you understand them better. All right, let me erase these things on the screen so that it doesn't block our view. All right, let's get back to the slides. So I've already given a brief idea of what well logging is all about. So we'll just look at what are the possible definitions that we have for well logging. So a well is only a hole until it is locked. It's only a hole. If it doesn't lock it, then it has no geological significance. You can only attribute geological significance to it after it has been locked. So a well logging, also known as borehole logging, is a practice of making a detailed record of the geologic formation penetrated by a borehole. The log may be based either on visual inspection of samples brought to the surface. So we have what we call geological logs. These are logs that are brought to the surface during the process of drilling. You bring it in bulk and then you just try to analyze it to get the formation to see if you can get any imprint of hydrocarbon also. And then the physical measurement made by instrument lower into the borehole. So that one now, that's what we call the geophysical logs. The objective is to locate, define, and produce from a given reservoir. So let's get through some other definitions like a log. What's a log now? A log is just simply that record, the record made when the sensor now is sent into the formation. And at the gradual process in taking out those parameters from the reservoir now, it produces a curve, which we are going to see. This particular paperwork now is what we call a log. Porosity, definitely we know that is the amount of pore spaces within the formation. Permeability is the ability to transmit fluids. Water saturation is the amount of water within the formation. The resistivity, I've taken time to explain that, is the ability of the rock to conduct electricity. The net to pay, we are going to see that down there. So that net to pay, I will not dwell on it. There's a diagram down there, we are going to see it. The gross pay, also we are going to see that. So this is actually how the logging process looks like. So we have the wireline log, we have a wire tied to a tool, and this tool now we have a cable that is holding that particular tool. And then once you take it up, it starts measuring the physical properties of the log of the well. All right, once you now have the data at the end of the day, this is what you may now have to interpret. You have something that looks like this that you have to interpret and make sense out of it. All right, so these are the various types of offshore rigs that we have to drill the wells, because you cannot log if you don't have a well. In order to have that well, you need to undergo drilling. You need to undergo drilling. So these are the various types of rigs that we have. So this is how the process of taking this measurement actually looks like. We have a road-going logging vehicle where this wire is attached to it. The vehicle now moves at a predefined speed, because if you take it faster, you might not have good measurement. If you take it very slow, still you might have measurements that interact with each other. You may not have a good picture of how the reservoir looks like. So the speed of this vehicle has to be predefined by specialists. Okay, after the measurement must have been made, you now have processing that has to take place. And part of it, you have the data check, the depth shifting, the removal of end effects, SP baseline shifts, the rescaling, the patching, the block editing. Most of these things, the software will handle it. The software will handle most of these things. The software will handle most of this processing, because you also cannot make good interpretation. What's happening? You also cannot make a good interpretation if all of this processing, if all of these processes are not made. All right, so in the borehole environment, yeah, this is exactly what I was explaining about the invasion. This is how the borehole environment actually looks like. You have fluid that has penetrated into the formation, you have the invaded zone, you have the transition zone, and then you have the uninvaded zone. So all of this, we have the uninvaded zone is located beyond the invaded zone. So first, we have mud cake that is produced. I've already explained the aspect of mud cake. We have mud filtrate. These are the fluids that filtered into the formation during the invasion process. So part of that mud that filters, the liquid part of that mud that filters into the formation is what we call mud filtrate. Then the zone that has been affected is what we call the invaded zone. So definitely you are going to have different properties in these different zones. We don't expect the resistivity of this zone to be the same as the resistivity of the uninvaded zone. Because if part of the mud filtrate has penetrated into this zone, it's going to tamper with the fluid nature of this zone. Part of the water or the hydrocarbon must have been pushed away from this zone for the mud filtrate to occupy this zone. So the resistivity of that zone definitely cannot be the same as the resistivity of the uninvaded zone. This is still a picture of the invasion effect. All right, so all of this now is just an explanation of the drilling process and how the invasion takes place. All right, so let's get now into formation evaluation. What are the various ways in which we evaluate the formation? One of the first way is mud logging, because you know that during the drilling process, what happens is once the mud gets down there, even though we have said part of the mud is lost due to this overbalance effect, it is not just all of it, just a small amount of the mud is lost during this overbalance process. So what happens is the mud now recycles and goes back to the surface. The particles that the mud carries is filtered out of the mud, and then the mud now goes back into the mud tank and it is pumped back into the well. So that is how the process goes. So when these particles that are brought out from the well can also be analyzed to see if it can give us any information about the reservoir, about the fluid nature of the reservoir. So that process is what we call mud logging. Logging while drilling now, there are also sensors that are attached to the drilling string that the purpose of it is to get some kind of pre-measurement before the actual well log now takes place after the drilling must have been done with. So those sensors now, the measurement is what we call logging while drilling. Then wireline logging now is what now we are talking about, which is a conventional logging. It's a conventional logging where it is done after drilling must have taken place. It can be done before completion or after completion, because we have open hole logging and we also have the case hole logging. So these are the various information that we can get from the various types of log. the mud logging, the logging wire drilling, and the wireline log. All right. So the depth of investigation also is of great importance, because if you want to get a good picture of the reservoir, you need something that will actually measure far away from the invasion zone, so that you are now talking of the reservoir itself. The properties that you're measuring are the actual properties of the reservoir, not the properties of the invaded zone, not the properties of the invaded zone. So the depth of investigation also is of great importance. So you can actually see what happens. Induction log also is a type of resistivity log, but it is mostly done in a cased hole. It's done in a cased hole, because what happens is the process of generating electromagnetic waves. It generates waves, that these waves travels into the formation. And then these waves that are generated now creates electric current within the formation. So there's a whole lot of process that takes place during the induction process. All right. So this is where the key is. If you look at what we have here, it gives you an idea of the basic types of log that I've already mentioned above, what it actually measures, and what are the application. If you have you see the gamma ray, it doesn't need a source. So it measures natural phenomenon. You just need to drop down the sensors, and the sensors measures what is already in the reservoir. It's not like you have to stimulate it with something. So it measures natural radioactivities, and it's mostly what? Uranium, thorium, and the potassium. But generally, the gamma ray law measures the overall effect of these three radioactive material. But if you want to get now the individual effects, you now have to carry out what we call the spectral log. We are going to see that as we go down. So what are the applications of gamma ray? We have the sun-shield differentiation, differentiate between sun and shield. So from there now, you can actually know what is your reservoir and what is not your reservoir. So we go now to the density log. It is still gamma ray, the source. This time around, we have a source, which is a gamma ray source. And then what does it measure? It measures electron density. I don't want to go into that because we are going down to the next thing, which is gamma ray. I'll explain that. So it measures what? It's a measure of what? Porosity. You can also use it to differentiate between sun and shield. You can also use it to differentiate between oil, gas, and water. So the neutron log, what does it measure? It measures, what source does it take first? You have to emit high energy neutrons into the formation. And these high energy neutrons now collide with hydrogen mostly. I'm going to come to that. So let me not talk more on that. So it measures the hydrogen effects. It measures the hydrogen index of that formation. So it's a measure of what? Porosity. It can also be used to differentiate between sun, shield, and all of gas, oil, water, and all of that. So sonic now measures the transit time, the time taken for waves, P waves, and S waves to travel from one source to another, from one receiver to another receiver. That's why they call it a transit time, because we have two receivers. What they're actually measuring now is the time difference between the first receiver and the second receiver. And then we have the resistivity, which I've already talked more on that. All right, so let's go now to the gamma ray. So what happens now with the gamma ray is we have, all right, so we have a sensor, we have our sensor then. You have a source, then we have, this is what measures the overall effects. So the source emits gamma ray into the formation. The gamma ray collides with particles within the formation. As it collides with particles within the formation, part of the gamma ray is deflected. So when it collides with this, for example, is deflected. If there's one that goes in this direction, is deflected to the receiver. If it goes like that, it's deflected to the receiver. So the more particles we have within the formation, the more deflection we are going to have. So this density log actually measures what we call the electron density. The more electrons we have within the formation, the more deflection we are going to have. So if we have a very porous formation where the particles lie in this manner, what we are going to have is we have some gamma ray that will actually go through that particular formation undeflected. That's why we said it is also a measure of porosity. It's also a measure of porosity. If you look at what we have here, it's a measure of porosity. When we start the practical section, you realize that the density and the neutron log is under the porosity log. So this is the general idea of what the density log is. All right. First, let's look at the gamma ray, because the first thing you go to an area is you want to identify if there is any reservoir in that particular area. And we know what reservoir rocks are. They are rocks that are porous, and we expect this rock to either be what? Either be sandstone, either limestone, or in some cases, we may also have dolomites. So we have said the gamma ray measures the natural radioactivity, which is uranium, thorium, and the potassium. So the problem now is, what is the variation of these various elements within the particular formation? What do we expect it to be? How do we expect the variation to be? All right, so if we look at this, we have gamma ray are bursts of high energy electromagnetic waves which are emitted by atomic nuclei as a form of radiation. It's a measurement of natural radioactivity in the formation versus depth. It is also known as the shale log. All right, so you are also used to indicate shale. So used for correlation, you determine bed boundaries, you determine the gamma ray log. This is the scale. I'm not going to talk about the scale now. We'll talk about it better when we start the software. All right, so I mentioned something about the gamma ray spectrometry. We may have formations where at times you may see a high reading of gamma ray, and you expect that that high reading is going to be in a shale formation, but it is not in a shale formation. So the problem now is you have to find out what is actually happening. Because if I have a formation, if this is my sandstone, for example, and this is my shale, I expect that my gamma ray should be low here. And then when I get to the shale, I have a high gamma ray. Why is this reading high? Because of high uranium. And this high uranium is due to what? Is due to organic matter that is found in shale. The uranium is one of the main elements that causes that difference between sandstone and shale, because it may be difficult to distinguish between the potassium content of sandstone and shale, because we may have a sandstone that is rich in feldspar, which we have feldspathic sandstone. You may have clays in shale that have high potassium content. The same also with thorium. There is no clear demarcation between sandstone and shale when it comes to potassium and thorium. So what will cause this high difference is the uranium nature, of the organic matter that are found in the shale. That is what causes that difference. But you may have a situation where instead of having low gamma ray here, you may have high gamma ray. Then you now start asking yourself, probably you already know the stratigraphy of that particular area, and you start asking yourself now, what is happening in this particular area? In that particular case now, you need to carry out what we call gamma ray spectrometry, where you now measure the concentration of each of these elements separately You have potassium, you see the variation of potassium. You have uranium, you see the variation of uranium. You have thorium, you see the variation of thorium. So when I get now into this particular formation, if this high measurement is coming from potassium, then I'll probably know that this is a reservoir rock, but the high measurement is due to probably a lot of feldspars that are found in that particular sandstone. That's found in that particular sandstone. Because definitely, I will also look at the uranium, and if I see a low value for uranium, that also confirms the fact that this is a reservoir. So this particular measurement is done in area where you have some doubts about the gamma ray values. So you have to carry out the gamma ray spectrometry where you measure each of these amount. So you have to each of these logs separately so that you can actually make a good interpretation. All right. So NTG application, the natural gamma ray spectrometry, we have lithology identification, study of the positional environment, is investigation of shale types, correlation of gamma ray, and so many other aspects. All right. The natural gamma ray log now is what we have already explained. It was so unfortunate that it came after that, but we have already talked about this. The uranium nature, what does it, where does it come from? It indicates what? A phosphate, organic matter. Organic matter, you have thorium indicate clay content, you have potassium indicate clay content, radioactive evaporites. We also have feldspathic sandstones and stuff like that. So in a sandstone, we expect that the thorium in a sandstone indicates clay content, it indicates heavy minerals. Potassium indicates micas, micaceous clays, and feldspars. This is exactly what I was explaining here about the NGT. So in a shale, I expect shale suggests source rock, definitely, and also the thorium there indicates the amount of digital material, and the potassium indicates clay type, mica, and so on. All right. So this averagely, this is what we expect the gamma ray value of these measured types of rocks that we are going to encounter in the field to be. Generally for limestone is less than 20, for dolomite is less than 30, sandstone less than 30, shale we have it between 80 to 300, salt less than 10, and anhydrite also less than 10. All right, so this is exactly what happens. This is exactly what happens when we have a formation. Let me erase this so that we can see it clearly. Let me take this off. All right, so if you look at what we have here, you realize that this is a shale that has a very high reading of gamma ray. We have a shaly sand, that means you have sufficient amount of shale in it. That's why the gamma ray value is moderate. Then we have a clean sand that has a very, very low value of shale. The fact that we use the term clean sand is a relative term. It doesn't necessarily mean that it has zero clay in it or zero shale in it, because there is no way you can ever have sand with zero shale in it. You must always have that contamination. But we use the term clean if the gamma ray value is less than 15, then you can now attribute it as a clean sand. All right, so this is what we actually have in the formation. That's what we have. We have our shale, we have the sand, and then we have another sand body here. We actually look at, this is what we'll be doing with the interactive petrophysics, to actually see where our reservoir is. Because if you don't know where the reservoir is, you cannot characterize the reservoir. You can only characterize what you know. So if you don't know that your reservoir starts from this depth and ends at this depth, there is no way you can characterize the reservoir. All right, so another aspect now is the net to gross. So what will generally happen is we may have this situation. You have identified this zone, this particular zone, as your reservoir. You have identified this particular zone as your reservoir zone. You have identified this zone as your reservoir zone, but you may realize that in the field, it might not just be clean in this manner. You may have a situation where you have a sharp increase here and it goes back down, then you have in that manner. That's what you may have. So what you may have identified as your reservoir rock or your reservoir interval is not purely reservoir. That means you have some intercalation of shales there. So what we are going to have to do now is to calculate the net to gross. That means in that interval that I have chosen as my reservoir, what depth actually represents your reservoir? That's what we call the net to gross. So I have chosen this entire depth as my reservoir. So if I've chosen this entire thickness as my reservoir, you now realize that this part of it is not a reservoir. This part is not a reservoir, and this part is not a reservoir. So we are going to take what we call the net reservoir, what is actually a reservoir within that interval that I've chosen as my reservoir. So this height, which we call H1 plus H2 plus, even though this is a shaly sand, but you may consider as a reservoir depending on the cutoff of that particular area. We are going to look at cutoff when we start the practical exercise. So we have H2, H3. This is what we call the net reservoir. This is what we call the net reservoir. So if, for example, this total thickness is 100 meter, let's take, for example, 100 meter, and then let's say this is 20, and then all of this is 40. It means that our net reservoir is 20 plus 40, which is what? Which is 60. I take the 60 divided by the total thickness of what I decided that was my reservoir, which is 100. I end up now with a net to gross of what? 0.6. That means in that particular area, what actually represents my reservoir is 0.6, or 60% of that interval represents my reservoir. No, it's not the entire depth that represents my reservoir. So that is what we call net to gross. All right, so it's the same explanation down here, All right, so when it comes to the volume of shield, we know that we have talked about the gamma ray log, that is used to differentiate between reservoir and non-reservoir, or here, let's just say shield and sandstone, because the more than 60% of reservoirs in the world are sandstone. So in this case, let's just use shield and sandstone to represent our the reservoir and the non-reservoir. So if you want to calculate the volume of shield, the best method to calculate the volume of shield is using the gamma ray. That's the best method of calculating the volume of shield. But what you're going to calculate from the volume of shield, because what you do is you screen through the entire log, you pick the minimum value of gamma ray reading, you pick the maximum value of gamma ray reading, you note those minimum and maximum value. You are going to use that minimum and maximum value for the entire calculation, because that minimum and maximum value doesn't change for that particular well. So what you do now is you go to each interval, you identify the gamma ray value at that particular interval, put it in this formula, then you now calculate the volume of shield. But in this case, I'll just call it the gamma ray index. Because it is not the real measurement of the volume of shield, because this particular measurement is always linear. It's always linear for an ideal situation, and we know that rocks in the earth does not obey the ideal law. So you have now to use this gamma ray index now to calculate the actual value of the volume of shield in that particular well. You may now have to apply different formulas depending on where you are, depending on your priority, depending on the age of that particular rock, and so on. So if you're dealing with tertiary rocks, especially like what we have in the Niger Delta Basin in Nigeria, then you may be tempted to use the Larinoff equation for tertiary rocks. So this is the formula that you now have to actually use to calculate the volume of shale, So let me take this off so that we can see it. We can see the formula clearly. So this is the formula that you may be tempted to use, but you can use the stable, the Clevial, and so many other formulas that you have. All right. So if we move ahead, now from there, now we go now to the spontaneous potential. It also measures natural phenomenon. It also measures natural phenomenon. That means you don't need a source for you to measure this particular log. So most of the time, we may be tempted to use just gamma ray to characterize the formation. But if you are having doubts in your measurement, you may now go ahead now to measure, to look at the spontaneous log and see what information you can also get from it. Of course, we can also use it to calculate the volume of shale. So you are now using the same idea that I gave. The same idea that I gave. So we have the spontaneous potential for clean. We have the spontaneous potential for shale. For shale. And then this one now is a spontaneous potential at the particular depth of interest. All right, so if we look, the caliper also is another log that can help give you information about the lithology, because it measures the diameter of the well. It measures the diameter of the well. So it tells us, it can give us a good idea about what lithology you're going to have. Because we expect that at a certain area, the diameter is not going to be continuous. In fact, it's practically impossible for the diameter to be the same from top to bottom, because we may have curved in some areas. We may have part of the formation may have collapsed and so on. So we don't expect the diameter to be the same. All right, so we are going to explain this better when we are doing the practical. This one was just for you to have an idea of this concept, so that we don't just get into it and you're now asking, hey, what's gamma ray for? What is resistivity for? And all of that. So resistivity, I've already taken time to explain the resistivity nature of the formation. We don't need to go into that. This is exactly what I explained. The conductivity is inversely proportional to the resistivity. So I've already taken time to explain the concept of resistivity. All right. So even porosity, I think we have talked more on that. I think I'm looking, okay, all right. So this is the density log. I've already explained this. So I'll just brief through it so that we go ahead. So I said for the density log, it is also called the gamma ray is also called the gamma ray log, because there is a source that emits gamma ray. This gamma ray interacts with the formation. As it interacts with the formation, part of it is deflected. Those that are deflected are now measured at the source. And they are measured at the receiver. That's why we call it gamma ray. You send in gamma ray and you measure gamma ray. So the more the gamma ray collides with particles in the formation, the more deflection takes place. So it actually measures the electron density. The more electrons we have within the formation, the more deflection we have. So if we have high deflection, it means that we have high amount of electrons within the formation. Definitely, we expect the porosity to be what? To be very low. So let's not talk more on that because we have already elaborated on that. So density, the use of that. All right. So you use the density to calculate the porosity. So this is a brief There's a formula that can be used to obtain the porosity of that particular formation. All right, so if we go down, all right, so the neutron lock, what happens with the neutron lock is we also have a source that emits neutron. I don't want to get into that. All right, since there's no diagram for that, let me illustrate. We have a source also. We have a source that emits high energy neutrons. These high energy neutrons are called thermal neutrons. They are called thermal neutrons. These high energy neutrons collide with particles. Definitely when it collides with particle, part of the energy is transferred to the particle. The particle also speeds up, and then this neutron slows down. It may slow down to a point where we may have approximately 10 electron volts of energy. That particular point, we call it the epithermal neutron. The epithermal neutron. So when this neutron slows down to a particular level, it actually emits gamma ray. It actually emits gamma ray. So we have a receiver here that can actually measure three things. So it depends on the company. Some company will design the receiver in such a way that it measures the amount of thermal neutron. Other companies will design it in such a way that it measures the amount of epithermal neutron. Other companies will design it in such a way that it measures the amount of gamma ray that is emitted. The amount of gamma ray that is emitted as the neutron slows down. So those are the three things that can be measured. So what you note now is that the slowing down of the neutron depends on the mass difference between the neutron and the particles that it collides with. If they have almost the same mass, then the slowing down becomes very great. It slows down at a very high rate. So a neutron and hydrogen has almost the same mass. Has almost the same mass, and it has almost the same size. So when it collides with hydrogen, it slows down faster than any other particle within that particular formation. So it is always termed that nitrogen measures what? The hydrogen index. It's not as if it doesn't slow down when it collides with other particles, but the slowing down is not as fast as when it collides with hydrogen. It's not as fast as when it collides with hydrogen. All right, so let's move on. So this is typically what we may have, what we may see when we have all these logs put together. First, we have the gamma ray. All right, the gamma ray
Thank you very much. Please, we know we have taken a little bit of time. We are rounding up. Actually, the administrative director of Josephus has taken his time to go through the whole thing step by step, and I believe that you guys have gotten it very well. So what you're seeing actually on your slide now is just what he has been saying from the beginning till the end. So you have a gamma ray lock, you have a neutron, and then you have a resistivity lock. You can still reverse it. You can have a gamma ray lock, you have resistivity, then you have a neutron density lock at the end. In that case, we usually call that a triple combo. When we arrange it like that in threes, we call it a triple combo. So normally, you see that immediately you pick your well lock and you load it into your software. The first thing you're looking for is you're looking for a reservoir. And when you look at this first lock, you can see that that's a reservoir. Why? Because of low gamma ray values. I mean, low radioactive, very high radioactive elements. and then with very low radioactive elements. Consequently, they have very low gamma ray values. So it's a reservoir. It's sandstone that have those qualities. And then when you have very high radioactive elements like this, high gamma ray values, is definitely shale. So that's how we pick our reservoir in a well. Once you pick your reservoir in a well, because that gamma ray, we usually call gamma ray the lithology log, right? So it differentiates between what is sand and what is shale. That's the main function of a gamma ray log. You can have gamma ray log, you can have caliper log, and you can have spontaneous potential on one track. We call that track the lithology track, because it all defines our lithology. Very, very necessary. We cannot even start without knowing what is sandstone and what is shale. We must define that first before we continue. Immediately we define what is sandstone and what is shale. We then move to know now within those reservoirs, those sandstone that you have picked, because your interest now is now the reservoir. Within those reservoirs that you have picked, you are now moving to resistivity. Now, resistivity will tell you what is gas and what is, hydrocarbon and what is water. We know that we are so much interested in hydrocarbon. In any reservoir, there is always water. So we want to identify what is hydrocarbon and what is water. And we know you and I, my colleague has taken his time to explain to you what resistivity measures. When you look at the resistivity value there, the scale there is showing you from 2.0 to 3. So it can still be 0.2 to 2000. It increases from left to right. So it means that resistivity in your log increasing from your left directly to your right. That is how your resistivity increasing. Same like your lithology, your gamma ray, it increases from your left to your right. So anytime you see values that are increasing towards your right, then you know that that's increased resistivity values. An increase in resistivity values identify the presence of hydrocarbon in your reservoir, while a decrease in resistivity values indicate the presence of water. We know that resistivity is the reciprocal of conductivity. So if definitely water has a very high conductivity, then the resistivity will be very low. That's why when you look at this log, you will see that it differentiates clearly between what is hydrocarbon and what is water. You can see it here. This is hydrocarbon, higher resistivity values, and a decrease in resistivity values here induces the presence of water. So you need to know that. So once you are done with that, the next thing you move, the next track that you move to is, we call this the porosity track. Within this porosity track, we have the neutron and the density log. Still, my colleague has taken his time to explain to you detailedly what the neutron and the density log measures. Yeah, so within this porosity track now tells us within that hydrocarbon, what is oil and what is gas. Remember that it is very valuable for us to differentiate between what is oil and what is gas. Once you know the density and the neutron values, you can have a cross plot of neutron and density. And that cross plot is going to give you the presence of gas and the presence of oil. If you do a cross plot of neutron and density and you see a balloon effect, you are going to identify the presence of gas within that reservoir. If you do that cross plot and there is no balloon effect, now when you look at clearly, you see that this is a balloon effect within this cross plot. And so that is the presence of gas in your reservoir. And when there is no balloon effect and there is no cross plot between those two, you know that it signifies oil. So that is how we qualitatively differentiate between oil and gas within our reservoir. Even though sometimes when we calculate the density, it tells us already that this is oil and this, because we know the density of oil and we know the density of gas. But physically, if you want to differentiate it qualitatively, you need to see this balloon effect. I don't know if we are going to get into the details of this balloon effect and what it causes, but you realize that once you get into an environment that is gas, what happens to neutron? Neutron decreases. Neutron value decreases. And if you are entering into an environment that is gas, what happens to density? Density value also decreases. Because you have done a cross plot, what happened? Those two values are going to cross plot at a particular area. And then you are going to have that balloon effect. So that's why you have that balloon effect. It's very, very clear there. Very, very clear. So it's so simple. This thing is so simple to understand. And so, I mean, it's so organized. And immediately you put your logs in this order, from lithology to resistivity to porosity log. It comes out very clearly and very simple for you to differentiate from what is reservoir to what is hydrocarbon and to what is oil or gas. Okay. Okay. So sonic log. So we know that sonic log measures the travel time and in sound through the rock record. So it measures it through microseconds per foot or per meter. And the rock properties can also be employed for sonic measurement. It can also be used for porosity. We can also understand lithology, gas show, compaction, and rock strength. We'll see most of that. We can also use it to tie our seismic to our well. And we can also create an acoustic impedance that will help us for well log calibration. That is what we use sonic log. Also, we can have some of those cross plot that we can do between sonic log and density, sonic and neutron, that will give us actually different properties. So from all what we have been talking about during our practical session, definitely it's very obvious that we are not going to go through all of this in just a couple of hours that we'll have tomorrow, but we are going to do as far as we can go. So we have tomorrow, we are going to look at qualitative assessment of reservoir properties, which is fluid type from the log pattern. And then we are going to have quantitative or numerical estimation of reservoir properties vis-a-vis percentage of oil. So we have qualitative interpretation, and then we have quantitative interpretation. So the first step, I mean, this diagram is so explanatory, self-explanatory. So basic step for quick look evaluation. The first thing is like you have your lithology track, which has a gamma ray, it has the caliper, and has a spontaneous. So it differentiates between what? You have the rock, so it differentiates between what is a reservoir and what is a non-reservoir. That is a lithology track that I've already talked about, and that's the job of gamma ray. That tells you what is a reservoir and what is a non-reservoir. The second partner here is your resistivity. Your resistivity now comes in to tell you, the resistivity track now, which is the second track, will tell you what is your hydrocarbon, what contains hydrocarbon, and one contains water. And then you have now that last track, which is your porosity track, which tells you what is gas bearing and what is oil bearing. From there now you can do your interpretation and do quantitative analysis in the software. I mean, so simple as that you can have. So from there we can calculate water saturation. So if we can calculate water saturation in a reservoir, then anything that is not water is definitely hydrocarbon. So hydrocarbon saturation now becomes 1 minus SW. So if SW is 0.5, then hydrocarbon saturation becomes 0.5 or 50% within the reservoir. So we'll go through all of these steps that you see, quantitative log interpretation, we determine everything, determine permeability, we determine the volume of shale, calculate uninvaded zone water saturation, determine whether the water saturation is low enough for water-free completion. We will calculate the true porosity of the zone, determine hydrocarbon saturation, and whether hydrocarbon are movable or not. We will determine the permeability. We calculate the net to gross pay. So all of this method, so some of these methods used in establishing this parameter includes the Archie equation, the ratio method, the Pinkett and the Hingel cross plot, the neutron density cross plot, the Indonesian. All of this we will use for in the software. I mean, it's so simple with interactive petrophysics to do all of this. Permeability will be done to calculate permeability. Your different method of calculating your water saturation will be used. Clean shale, hydrocarbon, recoverable, movable, everything. And we'll follow this workflow for our analysis. So the first thing is the data collection itself. We load our data, we QC our data. If we QC our data and our data is okay, we continue, we do well or correlation, depth shifting, identification of reservoir. So we follow the whole of this process right up to fluid presentation, final presentation, sorry. So that's the process that we are going to have tomorrow. I will just leave my colleague to. So we'll normally, but at this point in time, we are going to take questions. We are going to take questions. So